Projectile motion is a topic that students year after year seem to find very challenging, and yet it shouldn't be too difficult because you know how to do all the different processes you need if you can break the problems down into the right parts in the right ways. And so this introduction to projectile motion is designed to help you to see how you can and should break down your projectile motion problems into the different parts. We'll start off by telling you what projectile motion is. It's the motion of an object that has been shot, launched, or thrown, and it's not under its own propulsion. Now, you could have a projectile under its own propulsion, and you could later on we could combine various things we've learned and solve that kind of a problem, but this is the simpler version of projectile motion. Here we have three pictures depicting launchers or ways of producing projectile motion. This one on the left is actually a trebuchet, and you can see that after it reaches a certain point, the ball is no longer under the power of the trebuchet. So it is after a certain point, it is just at the mercy of gravity and air resistance. And by the way, we will most often just neglect air resistance in these problems. But after the ball or projectile leaves the trebuchet cannot exert any more force over it. Same thing with the ball that is being pitched here by the pitcher. Actually, we need to add a caveat there, something that we're going to neglect in most cases, which is that this ball, baseballs, if you've ever held one or played with one, or even a softball, they have ribs on them from the string that's used to sew up the leather that makes up the outside of the ball. And that string, those ribs, can be spun so as to give the ball a certain amount of air resistance. So in actual fact, because of air resistance and because pitchers can make the ball spin certain ways as they release it, the spinning ball with those ribs will actually be exerting a force against the air, and the air will be exerting a force against the ball in the opposite direction, and thus you can have a little bit of lift sometimes because of the spin, or you can have some curving because of the spin. And, those are effects that we're going to neglect as we treat our projectile motion, unless the problem tells you not to neglect them. Likewise, with a bullet, you can see this high-speed photography picture of a bullet just as it leaves the barrel of a gun, and we usually treat the bullet as if its time of acceleration is from its rest at the beginning, back at the back of the barrel, to the time that it leaves the barrel. But you can see here there might be just a little bit more force being exerted by the gases that had propelled it while it was in the barrel. There might be a little bit of force being applied over a very small distance after the bullet leaves the barrel of the gun. But you can see how the pattern of those gases spreading out means that not all that force keeps being applied to the bullet, and not to the same extent as it was while the bullet was in the barrel. So what we get out of this is that, well, first of all, we're going to neglect whatever effect there might be after the bullet leaves the barrel. That will also simplify our lives. Again, all these things that we're neglecting, as physicists like to do, are just to simplify our lives. And usually we don't neglect things unless their effects are fairly small, and we will be pretty close even when we neglect the effect. So you will see, if you ever want to try to take into account all these extra things, the air resistance and the spin and the drag related to the spin on the ball, life becomes quite a bit more complicated. But still, you'd have to break down projectile motion problems in the same way we're doing just to even be able to begin to solve the problems. In order to learn how to break these problems down, we're going to first consider a simple projectile motion scenario. Very simple. A person standing in a huge train car. The train car is stationary on a straight level track. The person throws a softball straight up inside the train car and then catches it at exactly the height from which she had released it. So here's our simple depiction of a train car. Here are the wheels of the train car. They're sitting on the track. Here's the outline of the train car. We'll say, for the sake of our hypothetical scenario, that it's got glass walls. And so she, being a person who's not going to throw the ball up until it hits the ceiling, can throw a softball anyway inside this train car. And so here's what that scenario would look like. She's going to throw it straight up, and it's going to come straight back down into her hand. Again, we reiterate that the train car is stationary. She was stationary relative to the train car, and the ball left her hand, went up, and came back down and was caught at exactly the height at which she had launched it. So our initial horizontal velocity was 0. Our initial vertical velocity of the ball when she released it was 15 meters per second. Obviously, as it went upward, it was slowing down. Why was it slowing down? Because it was being accelerated in the downward direction by gravity. And so eventually that initial velocity that it had was brought to 0, and that was at the point where the ball was at the highest point in its travel. And then the ball began to fall and speed up on its way back down. And so eventually it was going pretty fast right before she caught it. Okay, we need to ask ourselves, to the view of the person who threw the ball upward in the train, what was the path of the ball? Well, to her it seems the ball goes straight up from her hand and comes straight back down into it. She didn't have to move her hand forward or backward or side to side. And once she released the ball, she could hold her hand at that spot where she'd released the ball, and the ball would come right back down into it. How about the perspective of the person standing outside this train with the glass walls? If they watched this event, what would their view of the path of the ball be? Well, it would be the same. They would say, well, it looks like the ball left the girl's hand, went straight up, came back down. The girl didn't have to move her hand forward, backwards, left or right to catch it, and so the ball landed right back in her hand at the spot where she had released it. Well, what was going on during the flight of that ball? Time was passing. Time was ticking by. It took a certain amount of time to go up and come down, and we can calculate how much time it would take. And I've done all those calculations for you. I'm not going to show that in this PowerPoint. It'll be something we'll do as a separate exercise. But you can see the initial displacement of the ball right as it left the person's hand was 0 meters high. And as time went by, the ball was going upwards. So, by the way, a helpful hint is this. Think of this axis here, this y-axis of this graph, as the track of the ball. This is the dimension in which the ball was moving in this case. It's especially intuitive here because the ball was moving upward, right? So in the first quarter second, see, we have marked off a quarter second here. In the first quarter second, the ball had moved upward something like 3.5 meters here. More than 3 meters for sure. In the next quarter second, it moved from wherever that was to about 6.25. So it moved up a slightly smaller distance during the next quarter second. These plots, these points that we have plotted, are just like snapshots of where the ball was at certain times. Now, the ball was not out forward of the person's hand. It was right here at a half second. This is how high it was. At 3/4 of a second, it was here, something like 8.5 meters. I'm rounding off these numbers because I don't have them written down in front of me. And then at a full second, it was around 10 meters high, just slightly more than 10 meters above the person. So obviously that had to be a very large train car. And by the way, the drawing is completely out of proportion because unless the girl was really, really tall, the flight of the ball should look a lot higher than it did relative to her height. Okay, and then at a 1.25 seconds, we see the ball is at about 11 meters high. And at 1.5 seconds, it's nearly at its highest point, which is some point higher than 11 meters. And then I've added in, if you look, these time-wise, all these points so far have been 1/4 second apart from point to point. But this one here, I'll explain why that's there later. And this one also down at the bottom, I'll explain later why those are there. Actually, I was finding the highest point in its flight, which is called apogee, the highest point in the flight of a projectile. And we'll talk about and calculate that some other time. Okay, moving forward 1/4 second from 1.5, we go to 1 3/4, and we're back down to something probably just slightly more than 11 meters. And you can see the distances the ball is falling. It keeps falling larger and larger distances each second on the way back down. Indicate that the ball is speeding up on the way back down. It's being accelerated downward because gravity is still applying that downward acceleration. How about the horizontal position of the ball during its flight? Well, that seems like a dumb and boring question. It's obviously moving not at all. Its position is at 0. It's not forward or backwards or side to side from where it left the person's hand. It stays at the same position on an x-axis. If you had plotted an x and y axis and just put that over the top of the train car, again, the ball is going straight upwards. So now in this case, again, our y-axis is the track on which is the dimension we're talking about, and this y-axis actually is supposed to be representing horizontal motion. And since the ball didn't move any in the horizontal, it stayed in its original position the whole time through. It's very boring, but as time went by, it's still at position 0, still at position 0, still at position 0, still at position 0, all the way through. So we have no motion in the horizontal direction. That's what this graph is telling us. Or you could say a constant velocity of 0, which is, again, still no motion in the horizontal dimension.